Hi, my name is Reyna. My partner is Samantha Barrón, and we will be presenting in this video our proposal for the Maker Design Contest. And our team name is Team Epsilon, and our challenge was the electronic challenge. So the assignment was to create the interface between our battery, a 12-volt battery, and the motor or the electric motor that will be in the marker mechanism for the seat. So this motor had to receive a 24-volt signal, so it could work. So we had to create this amplifier circuit between our 12-volt battery and the 24-volt motor.
As Diego already said, we have the considerations of a system weight of 40 kilograms, a battery of 12 volts, and we have to selectionate a proper motor to move the whole system. This model have to be 24 volts, and the assignment is to design the connection between the power supply and the motor. The system has to be protected against current and voltage overload. So we are going to continue with our design. The proposed design, it has two sections, the amplifier and the regulator section. The motor we have selected is a gear motor of 10 revolutions per minute. It has a rate voltage of 24 volts. We need a nominal torque of 39.24 Newton meter. Meanwhile, this model only can give us 32. So we need a torque multiplier transmission with gears. This is really simple. For the amplifier section, we need an oscillator. With this configuration, we are using the 555 oscillator. It have to have a frequency of 1.2 kilohertz, and in this configuration. Next, we have
the amplifier circuit that, as Samantha mentioned, has the oscillator. We can see the oscillator in this section. This oscillator also uses inductors as well as a MOSFET transistor and a diode. So we can use these elements to create an amplifying signal because the changes in the current generated at opening and closing the transistor. So finally, we have this amplifier that has this output. When we don't have a charge, the amplifier has a tendency to multiply the voltage to infinity. But that's why we need a charge. When we have a charge in our system, the amplifier is limited. We can see that our amplifier has a signal between 25 and 24 volts around it. So this is enough so we can pass it to the rectifying circuit. That the rectifying circuit will be explained next by my partner Samantha.
For the regulator section that controls the output voltage for the electric motors, we have a regulator center with a center diode of 24 volts and the max current output of 2 amperes.
Well, having explained the parts of our design, we can go to the simulation to create a simulation test for the design considering our motor. So let's go to the simulation. Well, we are now at the simulations. So as we can see, this is the main parts of our design. This is basically the whole design. We have as input the battery from 12 volts, and we also have our output. For example, here is the oscillator we mentioned before. Here is the amplifier phase, and here's our rectifying phase. So we can create a simulation using this charge, this resistance. The resistance was calculated taking into account the 33.54 watts of power that our motor receives, as well as the 24 volts that it will receive. So we create this charge that we ask for a similar current to that one of our motor. So if we create in our simulation and transient analysis with 1 second, because this will plenty of time enough to see all the effects that will happen in our amplifier, you can see that the result is this graph for the current. This graph will tell us that we have around 1.5 amperes of current demanded by our resistance. And if we check for the voltage, if we take it as an output and stops displaying the current. We will see that in the same analysis with the same data, with the same time, we'll find that the voltage of our regulator and our amplifier will be around 24 volts. As we can see over here, it's 25 volts. That is around a volt higher than what we expected, but this is to be expected because especially with our varying output from the amplifier, as we could see in the graphs that it was oscillating, this will generate us this kind of response. And we also have this interesting hump over here. This is actually an high point from our voltage expectations, but we can see that it's only 26 volts. So it's not that high of a difference, so it will not affect really our model. But it's also something we have to consider if we're going to put a really sensible motor, but the motor we selected is not that sensible. So this is all for the simulation. We will test next some other examples, but this will really only be seen in the resulting graphs. So this demonstration is not too long. And we'll go with my partner Samantha next to see one of these demonstrations.
To test the overload protection, which is a fuse of 1.6 amperes, we simulate our circuit with a resistor of 12 ohms. This resistor asks for a 2 ampere current. As we can see in the graph, the power supply is we reach a 2 ampere output. This is because our fuse breaks with a current of 2 amperes, even though it is listed as a 1.6 ampere fuse.
Our final simulation considers a 4K resistor. This is so we can test our circuit when there is a really small current as from it. As we can see, our expected current was around 1 milliampere, and we can see that the result is around 1 milliampere. And also the voltage, it's higher than 24 volts. So this is a problem because our circuit supplies a higher voltage when we have a higher current, but that's why we expect 24 volt motor, and our expected motor is so that we never reach this kind of circumstances. So we always have a current around the current of the motor, even if we are using a controlling device like BMW circuit, the current will always be around this type of numbers like 1.5, 1.6 ampere. So we will never reach this situation, but this is our interesting simulation to test so we can see the effects the current has in our circuit.
Finally, we have the bill of materials for our design. We have considered to make a PCB print, and the price of this with all of the components is $21.86. The highest inversion in this design is the gear motor. It is $246. So the total design will cost $268. But is a great inversion because the motor with a great care of it will last long. So thank you. We appreciate this contest. See you the next.